Now today I'm very honored and very excited to have a dynamic speaker with us. I'm only going to say one thing that I thought would be very interesting. Some of you may not know about Bob. Back in 2008, Bob wanted to go to Africa. And it was a trip that he was dreaming all his life. And therefore, we had a meeting there, a climate forum meeting, and Bob and I went to Africa to attend the meeting. So after the meeting, Bob told me that the best place to go, not to go to the national parks to see the wildlife. In Kenya, there's so many wildlife there that people can go and see. But he wanted to go to high schools to talk with kids, talk with high school students. And in fact, so I had to arrange one school, which was a little bit a rural school. And we had to go there with him. And he spoke with a lot of fire. He excited the kid. And that was 2008. And he was fired up. And the kid was also fired up, I'm telling you. So he excited them, talked to them. And then later on, when we came back to the US, he was able to speak with a lot of friends and colleagues. And he was able to raise some money that he sent back to help those kids who are not able to attend school fees, to pay for their school fees. So please, let's give him a lot of applause.
Thanks, Charles.
I see that Thank you. Thank you.
Thanks, Charles.
So today he's trying to find a base here, as usual, and he has got a very exciting topic. Angel hair, whatever that means. And ice cream castles, he's also going to be talking about that, dripping faucets, and also Euler fractals. Please help me welcome our speaker, Bob Cahalan.
Thank you. Thanks, Charles, for that kind introduction, and thanks to you all for coming. Charles reminded me, actually, that was sort of a dual presentation that Charles and I gave. And it was on a Saturday, and these kids who were in a rural area all dressed up in their school uniforms and came in on a Saturday, which really impressed me. It was probably an audience a little bit bigger than this. And Charles and I each had a microphone, and we kind of walked among the kids and kind of worked them a bit. In fact, we started by handing a camera to one of them and said, take some pictures, but not just to your friends. Take a few pictures, then hand it to the next kid. So by the end of it, we had pictures taken by maybe a dozen different kids, and you could easily tell when a new person took the camera because people see things differently. I remember one student who was sitting in the back kind of slouched down and kind of hoping to disappear. Like maybe some of the people, is that you, Dongwoo? Dongwoo back there. Maybe like Dongwoo sliding back there was really one of the smarter kids in the group, and we got into a back and forth. Remember that? What was it about? It was about some theory of the structure of the lunar surface or something like that, and he was saying it might have been bubbles from boiling in the moon and things, so we were arguing back and forth. And he was being kind of challenging, sort of disagreeing with things that Charles and I were saying, famous NASA scientists, right? And at a certain point, we just sort of stopped and looked at each other and winked and said to the other kids, this is science. This is it. This is what we do. We argue with each other. That's how we get somewhere with our learning. So he immediately sort of looked kind of puzzled at first, and then I think kind of happy that he was part of that process. So I hope you'll contradict me as we go along here too, and don't hesitate. So let me say just a word about the topic, because it may have been a little confusing. The abstract, I know, was confusing, had some misspellings in it. That's because my background is not English, it's Irish. And so we always sort of try to do our best to warp the English language, and I think dinosaur with a dino Y is just better than the other spelling. So this is a stream on a farm in Pennsylvania, and it's an upstream cascade, upscale cascade, so like any stream, it joins with other streams. This particular one feeds Deer Creek, which is the last place where the only vertebrate indigenous to Maryland was seen in 1988. That's the Maryland darter. So we don't know if that fish is extinct yet or not. The International Union says it is, but Fish and Wildlife says they still hope to find it. But let me go to the title, Angel Hair Ice Cream Castles. You probably recognize that that's from Joni Mitchell's tune about clouds from both sides now. Both sides now is the title of the tune. So it's sort of looking at clouds, and I guess I've been doing that since I was a little kid. So that's sort of one of the themes. Dripping faucets is another theme. Even with a single stream of drops, it can get interesting, and it gets fractal, as we'll see. And Euler fractals. So let me say a bit about why Euler fractals. And it is sort of pronounced a little different than you might try to say it based on the letters. This guy, Euler, is one of the great mathematicians of the last couple of millennia. And maybe he still isn't widely enough known, surprisingly. I mean, not as well known as say, Euclid, but should be. You might notice that the eye on the left, which is his right eye, looks a little bit different, and he did from a young age have a problem with that eye. And then, but he had a very long career. I think I have the years here. Yeah, he was born in 1707 and died at age 76. And the last few years of his life, he was blind in the other eye also because of eye doctors back then were trying to deal with cataracts, and they weren't very good at it. So actually you can read about a lot of people around this time period, people like Bach and Handel, who died from complications of cataract surgery. In fact, Bach and Handel died from the same doctor's hand, a different doctor than the one who operated on Euler. Euler was born in Basel and studied, had sort of one-on-one studies with Jacob Bernoulli and one of Bernoulli's sons. Famous family for a long time, and you've heard of Bernoulli's law in fluid flow. And he, after he graduated from those studies, he hoped to get a job in University of Basel and applied to it, and was then offered a job in St. Petersburg, but said, well, let me wait to hear back from Basel, because I really prefer to stay at home. But eventually Basel turned him down. So he wasn't appreciated where he came from. So he went off to St. Petersburg, where one of the Bernoullis, there were two Bernoullis on faculty there, and one of them had passed away. So he was hired to take the other one's place. But it was not in the math department. I forget what it was. I think it was history or something like that. And he got there, and they quickly realized this guy's a mathematician. So they put him in the math department. He had a well-known doctoral student named Lagrange, and you've probably heard of Lagrangians. And that was invented working with Euler. Euler was the one who came up with what's called the action principle. And so you calculate the action from the Lagrangian. You can work out all the equations of motion. And originally at the time they were working, that was the Newtonian equations. But it turned out later on you could generalize this to relativistic and quantum mechanical problems. So a lot of what he did, he would start with the simple and find by generalizing that it worked for more and more complex things. Now I'm going to have one slide with a lot of math, and then almost no math for the rest of it. So this is the slide with the math. So there's a wonderful book that I recommend called Euler's Gem by Richardson in 2012. Euler's Gem is a theorem about what are called convex polyhedra. How many have heard of convex polyhedra? Who know what those are? Okay, there's a few of you, but not a lot. So one example is a cube. That's a convex polyhedron, a cube. It has, what, 6 faces, right, if you count them. And it has 8 vertices, 4 on top, 4 on the bottom. and then it has edges connecting those vertices, 4 on the top, 4 on the bottom, and 4 vertical going around. So 3 times 4 is 12 edges. And so using those 3 numbers, you can calculate the number of vertices. What did I say it was? 8, minus the number of edges, and we said that was 12. So 8 minus 12, that's minus 4 if I got it right, plus the number of faces. And if I got that right, that is what, 6? So minus 4 plus 6 is 2. So you get the number 2. Now if you take another one of these, for example, the one with the fewest number of faces, that's the tetrahedron, and you can do the same calculation, you get the same 2. If you take any of the others, the icosahedron, the dodecahedron, which has pentagons going around the faces, and the 5th one, you do any of those, but don't take something like this. That has a hole in it. And so you won't get 2 for this one. But there is a generalization. So what you do for this one is, instead of 2, you get 2 minus 2g, where g is called the genus of the surface. The genus you can calculate by imagining cutting along a closed path. So just take a pen, draw a closed path all the way around back to where you started, and cut with the scissors along that. The number of closed paths you can cut along without making the surface fall into 2 pieces, that's the genus. So obviously any closed path here, you cut around that, it would fall into 2 pieces. And that's true of any of the regular convex. But if you take this and cut around, say, one of the corners all the way around, it'll become like a cylinder. It won't fall into 2 pieces. And there are other paths on there. But at most 1, you can cut along 1 closed path. And so the genus for that is 1. 2 times 1 is 2. 2 minus 2 is 0. So if you do that same calculation with this, you'll get 0. Now, so Euler generalized this to all kinds of shapes and figures. By the way, in doing that, he's kind of inventing topology. So in topology, this donut is equivalent to this coffee cup. The 2 are no different. They each have 1 hole. And the kind of transformation you would make to turn this into that is called a homeomorphism. It's just sort of a smooth transformation without any cutting, without any tearing. So this equals that topologically. Also, any of these objects are equal to a sphere. So you can imagine kind of blowing this up until it rounds out completely and becomes a sphere. This is homeomorphic to a sphere. So that number 2 is not just a characteristic of those 5 things, but of the sphere. And the number 0 is characteristic of the torus. This is a torus. And that thing is called a topological invariant for a surface. It's an invariant. So it turns out that you can use that for all kinds of things, for untying knots and all kinds of topological problems. But that wasn't all Euler did. I mean, that book is all about just that one thing, Euler's gem. People sometimes talk about another equation of Euler's, e to the I pi plus 1 equals 0. That's another one that you could write a whole book about, and books have been written. But Euler first became famous by solving the Basel problem, which might be one that you would have done in homework somewhere in math. You sum up the inverse squares of all the counting numbers. So 1 over 1 squared, which is 1, 1 over 2 squared, which is a quarter, 1 over 3 squared, which is a ninth, keep going. Just add those up all the way to infinity. People have been trying to solve that problem for centuries. Nobody could do it. And then Euler came along and gave the answer. And the answer is pi squared over 6. Now pi, of course, had been known since Euclid, 2,000 years earlier than Euler. It's not only irrational, it's transcendental. So it's like more irrational than irrational. So how can you add up a bunch of rational things and get an irrational? That really puzzled people, and people banged on that for a long time, not believing it. But eventually it held up. It not only held up, but it was generalized, just like the other one, generalized almost beyond belief. And I'll just tell you one way that it was generalized. And that is that if instead of 2, n to the minus 2, you let that be, first of all, any integer, n to the minus s, where s could be 1, 2, 3, 4, 5. Now if it's 1, it doesn't converge. So you end up getting infinity. So he worked on other values of s, 3, 4, inverse cubes, and so on. And then in working with his students, he realized he could make s complex. So not just a real number, not just an integer, but any complex number with a real part and an imaginary part, like 3.2 plus I pi, for example, where I is the square root of minus 1. That is something which we now call the Riemann zeta function, because a guy named Riemann did a lot of work on it. Riemann, you might have heard his name because he invented the kind of curved surface geometries that Einstein needed when he developed general relativity. So Riemann did a lot of basic work. He actually only published 6 papers in his whole career, Riemann. Whereas Euler published a huge number of what are called folio volumes, which are oversized books. I think it's something like 80. They weren't all published while he was alive. About half of them were published after he passed away. Riemann, 6 papers, but each paper was a new area of mathematics that he opened up. So Riemannian geometry was one. Well, about this function, Riemann made a hypothesis or a guess. Now, first of all, Euler showed that that function can be written as a product of numbers involving the prime numbers. 1 over 1 minus 1 over prime to the s power. So you multiply all those over all the primes. Well, that tells you a lot about the function, because for every prime, there's a 0 in the denominator, and so a singularity in the function. And if you knew where those singularities were by studying the function, which you could study on the other side of the equation, which is a simpler version of it, and you find those places where it blows up, you'd know what the prime numbers are. Of course, that'd be nice, because any integer can be written as a product of prime numbers in only one unique way. That's the fundamental theorem of arithmetic. So Riemann said, I believe those zeros are all along a vertical line in the complex plane, parallel to the complex axis, and going through the real number 1/2. He said they're all along there. All the prime numbers can be found there, because that's where that thing blows up. That hypothesis has never been proven. We don't know if it's true or not. And it's never been disproven. We don't actually know. So actually, a lot of theorems that are known now are proven by assuming the Riemann hypothesis is true, and then you prove some theorem, and then you assume it's false, and you prove the same theorem. And so whether it's true or false, you've got your theorem. Well, another thing that Euler did was he looked at a particular group of numbers, prime numbers, called Mersenne primes. So those have the form, if p is a prime number, 2 to the p power, for example, pick a prime number like 11. 2 to the 11th power, and then subtract 1. Of course, 2 to the 11th power can't be a prime because it's even, right? It's 2 to a power, it's an even number. But if you subtract 1, it's an odd number, it could be a prime. Now it turns out for 11, it doesn't work. So it doesn't work for all the primes. But for some primes, it does work. And Euler had proven a theorem that even perfect numbers are ones where if you add up all the proper factors up to the number itself but not including it, you get the number itself. That's a perfect number. The smallest is 6, so factors of 6, 1, 2, 3, right? 1 plus 2 plus 3, 6. So that's a perfect number. So Euler had proven this theorem, but then Euclid came along 2,030 years later, or whatever it was, it's 2 millennia later, and he showed that every even perfect number has that form. So saying that something is an even perfect number and saying it's a Mersenne prime, those have a one-to-one mapping. If you find one, you find the other. Now, right now, 47 of them are known. You could be the person to find the 48th. And by the way, there's no known odd perfect number. We don't know if there isn't one. There could be one. If you find one, you're famous. You'll win a big prize. However, it's been proven this year that if you do find one, it has to be greater than 10 to the 1500th power. So it's a big number. It would take you a while. But again, 2 to the 11, it doesn't work with 11. 47 are known. Now, Euler also generalized the prime numbers. So a prime number is just one which you can't write as A times B, right? Because it doesn't have any factors. So Euler said, well, what's the next simplest kind of thing that you can't do something with? Well, let's call a number idonial, which is just a fancy Latin word for meaning convenient. Let's call it convenient. It's not a prime number, but it's convenient if you can't write it as A times B plus B times C plus A times C. So you take 3 numbers smaller than the number you're interested in, and you do that symmetric product, summing up the 3. So he defined that, and he said, that's convenient because if I could find some of those numbers, I can construct other prime numbers from those, even though those aren't prime. So then he started looking, and he calculated 65 of them. And then he couldn't find any more. The 65 are listed there. The largest is 1,848, is idonial. Now it's been shown fairly recently, like in the last decade, that at most one other can exist. So again, maybe you can find it. One other might exist. We don't know if this list is complete. There could be a 66th. But if the other one exists, then a kind of generalized Riemann hypothesis, not only the Riemann itself, but all such functions similar in some way to that has to be true. That was shown by Weinberger and some other people more recently. But again, 11 doesn't work. So 1 times 2 plus 2 times 3 plus 3 times 1 is 11. So 11 is inconvenient. It's not convenient. So just some things about numbers that Euler was involved in. And this is a picture of, on the chessboard, if you just start putting the powers of 2 on an 8 by 8 chessboard, 2 to the 0, 2 to the 1. And by the way, this comes from the Persian king who was so happy with the invention of chess. Maybe some of you have heard this story. He said to the inventor of chess, name anything, I'll give it to you. And so the inventor said, well, let's just take a chessboard, put 1 grain of wheat on the first square, and then 2 grains on the next square, and just keep doing that till you cover the chessboard. So the king said, oh, sure, go ahead, and ordered his people to do that. But after a bit of head scratching and trying to do it, they realized that by the time they got to the last square, even that square alone would have more wheat grains than they had in Persia, in the Persian Empire. And if you added up all the squares, you'd have more than you had in the world that you could produce. So just one of the examples of the doubling problem, right? The ones that are darkened there are the Mersenne primes. And Euclid got as far as 2 to the 31 minus 1. So you can calculate that one. He got that with no computers. He showed that was prime. And you see a bunch of them with little underlines, like 2 to the 11th. Those are ones where the number underlined is prime, but the Mersenne for that is not prime. 2 to the 11 minus 1, not prime. There are 9 of them underlined. So you can't count on the Mersennes. But let's see, did I list the largest? Yeah, right now, the 47th, the prime number to put in the exponent is 43,112,609. 2 to that power minus 1. A lot of digits there. By the way, that little square was published by Martin Gardner. Anybody know Martin Gardner?
Heard the name.
Martin Gardner, he was a guy who never took anything beyond high school math. He was, like my father, he was in World War II in the Navy. He came out of the Navy and he studied to be a journalist in Chicago. And so one of the first things he got involved with were what are called hexaflexagons. So you can take a sheet off the internet and cut this out and fold it. There's directions there. And you get a hexaflexagon. And by the way, Sunday was Martin Gardner's birthday, although he's been dead for, 3 years, I think. People still celebrate his birthday by building things like this. It looks like just a hexagon, right? A colored hexagon with one color on one side, one on the other side. And you make it out of just this straight. You cut this out and fold it, and then fold the thing until you get a hexagon. The only thing is if you sort of squeeze it together like this into 3 little pieces like that, and then kind of pry on the center of it, it pops open into another hexagon of a different color. And you can do that if you do it in the right order 12 times and get 12 different color patterns, and then you're back to the first one. If you do it in the wrong order, you'll get something less than 12. And this so fascinated a group of Princeton college students in sort of around just before World War II that they formed a little club. And one of the members of that was Richard Feynman. Another was John Tukey, you might have heard of. And the other 2 were well-known mathematicians, and they spent a lot of their spare time. Maybe wasted time, I don't know. So those are hexaflexagons. Martin Gardner, he now has, he wrote for 30 years a monthly column in Scientific American. Those were collected into 15 books. And you can now buy a CD for about $40 that have all 15 books of his articles, all in PDFs and all searchable. And that's where I got that plot. Mathematical games. So one other thing on this slide. Emmy Noether's symmetry conservation theorem. Emmy Noether was a female mathematician who had a harder time getting hired than Euler did, just because she was a woman. So this was in the 1930s, and she was invited to Berlin. She taught courses there, paid very little, and she was a top-notch mathematician. She proved the symmetry conservation theorem, which was used all through the 20th century, still being used in physics, which is each continuous symmetry. For example, continuous is like the homeomorphism. You can blow up a cube into a sphere. That's continuous, smooth. So each continuous symmetry of a physical system, and you can check whether it is by looking at the Lagrangian function and seeing if you can do a smooth transformation like a rotation or something that transforms it back to itself. So if you have one of those, and we'll give some examples, then there's a physical property of that system that's conserved, that isn't changed, like the number 2 in Euler's gem. It's conserved. You can do all sorts of transformations. For example, on the sphere, you can lay down any kind of network, for example, latitudes and longitudes, count up all the vertices and all the faces and all the edges, and you take that vertices minus edges plus faces, you'll get 2. Because it's a property of the sphere. It doesn't matter what network you use. So similarly, if you have some symmetry, you're going to get some conservation, like mass conservation, energy conservation, charge conservation, etc. Also, if you find something that's conserved by just studying the reactions of things, and you see something's conserved, you should be looking for a symmetry. Very powerful theory. And here's examples. So and I don't know if you can read that. Can you read that? I'll have to read it, I guess, because anyway, if it doesn't matter in the physics laws, when you start your clock, the 0 of time, only time differences matter, then energy is conserved. And we know it is, right? And remember, vice versa. So if energy is conserved, that tells you that only time differences matter. An interesting problem for people who believe the Big Bang. So you have to think about that a while. Turns out it still holds, but you have to really think about how you go right up to the Big Bang, the first 3 minutes or even shorter. Also, if there's a similar thing about space, that is, it doesn't matter if I start my coordinate system in space here or over here. All that matters is the difference in position. If that's the case, then momentum is conserved. Of course, we know it is, right? We do experiments and we test it. We find momentum's conserved. So that tells us, by her theorem, that it's only location differences that matter, not the absolute location. Now, of course, on the Earth, that's different because the Earth is spinning, so we're moving all the time anyway. So you got to kind of think about what that says for that coordinate system which is spinning. Also, if it doesn't matter what direction you're looking, you know, like if my coordinate system has the x direction from me over to Charles, and then I formulate all the equations, or now I change and it's from me over to Warren, who's got his eyes closed now, but open your eyes, Warren. So from me to Warren, and I get the same laws, even though I'm using a different coordinate system, then angular momentum is conserved. And if you do a bunch of experiments and you find, sure enough, angular momentum is conserved, like for a skater who's spinning around and then pulls her arms in and starts spinning faster, then your laws are rotation invariant. That generalizes to space-time. So if you combine time and space and you rotate in those coordinates, and actually time gets a factor of I in it, so you've got complex numbers actually. Those rotations are called Lorentz transformations, and the equations are invariant. So there's a 4 momentum vector with components energy and 3 momentum. There's also things called gauge transformations, and that's what people in particle physics look at. So this is a very powerful thing. So I just want to kind of dedicate the rest of the talk to those 2 mathematicians, Euler and Nether. And of course, Euler has the Euclid-Euler theorem. And if there's, Martin Gardner said, well, it'd be nice if there was another person whose name starts with EU who could prove that there are no odd perfect numbers. Then we'd have Euclid, Euler, and Eubanks or something. Okay, so 11 is a funny number, but I'm going to sort of sample what I've been involved in with 11s. I was born 66 years ago in central Ohio. 11 years later, I saw an aurora. 11 years later, I got married. 11 years later, I came here. 11 years later, I was involved with Landsat. And John's smiling now because he knows that. 11 years later, I've been involved in 3D radiation and starting in 1999, the Solar Radiation and Climate Experiment and the Lab for Atmospheres. And I'm not sure what's going to happen next now that we're 11 years later. Of course, so I'm just going to group these by which cycle. And the 1946 was the peak of solar cycle 18. So we've got, and I'm just going to label things between 46 and 56 as cycle 18, then 57. 57 was the big one. That's when I saw the aurora. That's cycle 19. And then 20, 21, 22, 23. I don't know what will happen in 24. I can't predict. And of course, this is what's been going on during that time. A lot has been going on, right? The Vietnam War and other things not shown on this. El Niños and La Niñas. We had the maximum solar cycle. The reds are El Niños, the blues are La Niñas, but things happen even during the gray years. For example, El Chichon and Pinatubo eruptions, which are shown there. Usually I talk about for an hour about this curve, but this is the only time I'm going to show this, and I'm not going to talk about it. So, but you all know this part anyway. It's pretty dramatic change. I mean, things have been getting hotter. And even studies funded by right-wing funding groups find that this is true, despite their best desire to see it's not true. By the way, it's not linear, of course. I just drew a straight line, but it's nonlinear. And there I drew 3 straight lines. And I'll show you an example where this is not an unlikely sequence where you get different slopes like that, even aside from the fact that we have several different forcing mechanisms, not only the greenhouse gases, but the volcanoes and the natural variability. It's not surprising that it's not all just a straight line, even if you didn't have those other forcings. Even if you just had global warming, it would not be a straight line, which I think is pretty interesting. And Ed Lorenz knew why quite a long time ago, like 50 years ago. So this is me in cycle 18. And which one am I? I don't know. I think Kathy and Marcy looked at it, and one of them, Marcy got it right. Yeah, but Kathy didn't. Kathy thought it was the guy with the teeth, right? He's got a good set of teeth. Actually, he's the one who sent me the photo recently. His mother was the Cub Scout sort of den mother. So these are Cub Scouts, and at that particular session, we'd made these barrels. The one I made is sitting over there, and I'm sitting on top of it right there, banging on a drum. So here I'm probably 8 years old, and I remember when I was 6 years younger than this, I was 2 years old, and I remember one of my earliest memories was I was saying, I'm 2 years old, and I said, oh, I could also say that this way. And then I remember, actually I was being potty trained at the time, and I held them both up, and then I brought them together, and I had this like eureka moment. And when you have those eureka moments, you're not always right, by the way. Sometimes you're wrong. But it turns out this is correct. Or does anyone disagree? Dong? What do you think, Dong? No, he's okay with it. All right, all right. I have real mixed feelings about mathematics. It looks like from what I've said so far, I'm crazy about mathematics, right? Actually, I hated mathematics at this time. And the reason was that I was in a Catholic school being taught by Catholic nuns who used mathematics, which they called a lollipop, as a punishment for misbehaving children. And believe me, I was a misbehaving child at this stage. Actually, I also was an altar boy for masses in the Catholic Church. So I put on the robes and everything and served the priest and so on. So if I had a picture like that, you'd think, oh, what a good little boy, you know. But actually, I was a troublemaker. And I got in trouble. And I got lollipops. And I got very good at math for that reason, that I was punished quite a bit. And as a result, you might not be able to see that, but they had like a multiplication bee, like a spelling bee. I won that in the school because I really knew those tables, because they'd give you these horrendous problems. So I hated math. But I really liked science because I liked to be outside all the time. I was in this little small town, population 10,000. We lived on the edge of town, and we were sort of the last house before the cornfields. And there were the cornfields, there was a golf course. My first job was as a golf caddy. So I was always outside, except when they made me sit in the desk, and then I was looking out the window and studying the clouds, and got in trouble for that too. So sometimes I broke windows, and sometimes I recruited people to break windows. And fortunately, when I did this isn't the actual bus that I did. This is a different bus I found on the internet. I don't have a photo of the one. In my own defense, I thought the bus was abandoned. So I didn't think it was one that they were about to use as a school bus. Turned out it was only being used by a construction company, and they weren't happy with this. And so me and the two kids who I recruited went to jail for a few hours. So we were behind bars. And fortunately, I got bailed out and learned a good lesson from that. And the person that bailed me out is shown here. That's my father. This is his Navy card from World War II. He and Martin Gardner were both in the Navy. And my father taught us semaphore, which was how to signal people with two flags. People from ship to ship would signal that way, or they'd use lanterns. He also claimed that that during the war, he had some special binoculars that could see at night, and I never believed him until much later when Henning Lydecker showed me a pair that worked like that and that were available in World War II, so who knew? And this is my mother. They got married during the war, 1944. They met at a Maryland naval base that now no longer exists, Bainbridge, Maryland, and got married in 1944. My mother then had a health problem. My father went AWOL during a hurricane to go up from Florida up to New York to be there when she was operated on. Fortunately, he didn't get put in prison for that in the brig because a friend of his moved the paperwork out of the line of the people who were going to be court-martialed. And I guess this is my high school picture. I want to mention my high school geometry teacher. I flunked my high school midterm in geometry, sophomore year. And I got 50% on it. And this guy, Larry Bogenschutz, called me aside and said, you know, you either left it blank or you had a very nice proof. So how do you work on problems? And I said, well, I just stare at the question until I see the answer and then write it down. And if I don't see the answer, I skip it. So he said, Bob, that's not going to get you very far. He said, what you should do is take a step, and then from writing something down, even if it doesn't get you to the answer, then take another step. And then you'll wander around, and pretty soon you'll know more than you did before, and you might see a short way to the answer. Just start doing things. Don't sit there and wait for lightning to strike. So that was a really good lesson. Also in high school, I built what's called a spirometer, which is a way of measuring lung capacity, and a strip chart recorder that records your breathing and things. So that was my sort of science project. Here's where I went to college, a small Catholic college in Cincinnati. We'd moved to Cincinnati. And lucky for me, but it was one of the top 5 small colleges in the country at the time, and had an NSF grant that allowed me to build an electron paramagnetic resonance system, and I started being paid for doing science. So that was when I started. I guess that was 46 years ago. Also with some friends built a plasma jet, wiring together about a dozen car batteries, 12-volt batteries, to make a plasma at high temperature, and then flowing gas through the spark region to make new materials. And to measure the current, we used a magnetometer in the space above where the current was flowing because you couldn't put an ammeter in there. So anyway, I always liked to sort of do things like that. And I started learning a lot of science in my courses there. And here's just a list of the things we all know, and that are really, when you think about it, pretty amazing things, and which most people who don't do science don't know. It's shocking to me, though, that people don't know this, these kinds of things. And you can just read through there a bit. And we all know all of those. It's kind of common knowledge in science. So I also wanted to learn guitar there, and I wanted to meet a brown-eyed girl, and I did meet a brown-eyed girl, and there she is. And when we graduated college, we got married and went off to graduate school together. And this is sort of our song by Van Morrison, an Irish musician. And this is the invitation to our wedding in 1968. And at the same time, we were watching the Democratic National Convention in 1968. You might remember that year, some of you, 1968. A lot happened that year, which I won't go over, but I will mention one thing. And so went off to graduate school, started studying physics at University of Illinois, and eventually met this guy who had just come from a postdoc at Princeton, advanced study program. And he had gotten his degree at Harvard under Julian Schwinger, who was one of the 3 people who won the Nobel Prize for quantum electrodynamics. Feynman was another one, and Tominaga. So I was his first student. And I almost left school and went out to California because I couldn't find anyone I wanted to work with until he came. So he was sort of my first real science mentor. And I started working on what are protons made out of? And then I published my first paper called Cluster Expansion, the Elastic Form Factor. It's just a way of saying what are protons made out of? And this assumes there's a cloud of virtual pions, which was the lightest meson known at the time. And actually comes up with a power law, which I didn't know is related to fractals, but that was the first paper I published in Physical Review in 1972. And also while I was there, I had a number of other good teachers, and here's one of them. I took a one-on-one study course with a guy named Wolfgang Haken. Here he is. And this is a colleague of his, Kenneth Appel. And I took algebraic topology from him. So I learned about all of these funny polyhedra and Euler and so on from this guy, just studying one-on-one. And after I finished it, Illinois, and just a few years after I left, in 1976, I left in 73. 3 years later, Wolfgang Haken solved the 4-color problem, which is a long-standing conjecture that you could take any planar map, like a map of the US or map of the world, use only 4 colors and color each area without having 2 of the same color cross at a boundary so that you couldn't distinguish them by the color. You don't need 5. And people thought that was true, but no one could prove it. And what he did was he proved that you only needed to check slightly less than 2,000 graphs. You didn't have to look at an infinity number of them. If you looked at just 2,000, it was 1,900 and something. And it was true for those 1,900 and something. It would be true for all graphs. And this other fellow then wrote a computer program that checked those 1,900 so that it wasn't done by hand. That was one of the first proofs that relied in a critical way on computing and not just on doing things on paper. A lot of mathematicians didn't like that, and they're still arguing over whether proofs like that are valid or not. But he was the one who did that. He was also fighting on the other side from my father in World War II, fought for Germany, had a limp from a wound that he received in the war. And I did learn to play the guitar while I was there. Started in college, but learned a bit more. This is a very good friend of mine, Sadri Hassani, who ended up having to leave Illinois, go back to Iran, where he had hoped for a sort of liberal change in the government. And when the opposite sort of change happened in Iran, he came back to the US and got his degree in Princeton, and now he teaches out at Normal University in Illinois, Normal, Illinois, teaches physics. So a good friend of mine, and these are other friends from Iran. And this is another friend of mine who lives in Florida now. So I'll tell you about one other friend of mine who took the qualifying exam the same time as me. His name is Don Licardello. And Don was convinced he would pass the test with no problem, and I was sure I'd fail because I came from a small college and didn't know all the fancy stuff. So Don, to make me feel better, made a bet that, and he said, whoever passes buys the other dinner. So I said, okay, at least I'll get a good dinner. But of course, it turned out Don failed, and he wouldn't let me buy him dinner. And he failed again after studying all summer, was forced out of Illinois, went to Virginia, took the qualifier there, and you could see that Illinois is much better than Virginia because he got the top grade in Virginia. And then he went to Birmingham, England, and had a postdoc, and then to Princeton, where he wrote one of the top physics papers of the 20th century, according to a collection that now exists. He was one of the gang of four who wrote a paper about scaling in solid state. A guy named Anderson was one of his, who Nobel laureate, was one of his co-authors. He then got a tenure at Princeton in physics, and then quit academia and started a company for online banking. He was one of the first to do that using some computing techniques, and eventually was CEO of that company called Princeton Telecom, then retired. He's now retired, living near Princeton. I wrote that story back to my advisor, Xiaojin Chang, who showed it around, and I said, Xiaojin, you know, you let me through and gave me a degree, and you kicked this guy out, and now he was CEO of Princeton Telecom. He showed that around to other people in the department, and they were very depressed, he said, because they try to design those tests to really make the right selection. And then my son Joel arrived in 1971. This is his first day of taking breath with Maggie, who's now up in Minnesota at a meeting giving a talk. She's just flying up there. And that's my second paper about producing something called a Z0. And this is what's called the standard model now, and the Z0 is one of those things. And then, of course, the Vietnam War was also part of the whole story. And we tried at one point to block a nearby Air Force base, unsuccessfully, and they arrested 38 of us. We did not spend more than, I think, an afternoon or maybe a day in jail, but both Maggie and I were at least together in the same jail. And this is one of the professors who was part of that. We were graduate students. So those things were going on at the same time. But back to this paper, I just want to jump to the present for a second. I've kept in touch with my advisor, here he is, and with his wife, who's a microbiologist. And unfortunately, the little girl that I knew as 5 years old at the time, well, fortunately, first of all, she grew up to become a best-selling author of 3 different best-selling books, but then got severe depression and committed suicide. And her mother has just published a book about her daughter called The Woman Who Could Not Forget. And that's because she wrote a story called The Rape of Nanking, which is about the killing by Japanese people of Chinese people in Nanking. And so my advisor and his wife now have an annual competition for young people, especially young women, to write about the influence of their daughter's writing on their way of thinking. And I went to the first, about 5 years ago, the first awarding of that, which took place in San Francisco. I was at AGU and I went over there. It was at the Japanese Cultural Center in San Francisco who hosted that meeting. And they awarded to a young woman from a microbiology department at Harvard, which is where Ying went to school, that award. So that happens every year now, and I keep in touch with both of them. So he was definitely a mentor. Right at the end of graduate school, I went to a summer school in Sicily. Here I'm doing something really stupid, which is climbing without ropes. I got away with it. Fate let me by that time. However, the fellow who took this picture came back that next weekend with someone else without me along, tried the same thing, and the rock came off in his hand and he fell down that cliff. Survived, but broke both arms and both legs. And took 4 hours to get them off of the place he landed. down to the hospital in Trapani below Ereche. And then he was flown back to Sweden where he recovered. He's fine now, amazingly. So I'm putting this symbol next to that. Don't try this, okay? Not a good idea. So skipping ahead, I went from there to Syracuse University. Here's Syracuse University in 1887. That's the university, and that's the observatory. Here it is more recently. This is the physics department, and I spent a lot of nights here in the Holden Observatory learning astronomy. So I learned where to find galaxies and stars. I learned all the constellations, observational astronomy. And then I went off to Western Kentucky University and taught astronomy and had both an observatory and a planetarium. This is a paper I wrote while at Syracuse, and my co-author there has kind of been in the news, unfortunately, because he got trapped in a sting operation in Argentina in this past January, and has since January been in prison in Argentina. And there's a group of people trying to help him. He now has 400 publications in physics and is a tenured professor, and by the way, he's still calling every week and guiding 2 PhD students back in the States and hoping to eventually get out of this mess he's in. So those things happen. Here's one other paper, and by then I had moved actually when this came out. But this is a paper with Lenny Susskind, who's one of the smartest people I ever wrote a paper with. You can find him in Wikipedia. And he is now head of the theory group at Stanford. And then this is still being referenced today by these authors. I think I showed you that, didn't I, Bill? This is the Phoenix collaboration. They're doing an experiment kind of based on what we were considering here. And this is a 2012 paper, and there are 432 co-authors. So I thought, for citations, shouldn't I be allowed to multiply by 432 here? But no, we don't do that. That's only one citation. So that one does get. And also, I used that topology that I learned in one paper. This was a student that I guided him through his thesis. This was part of his thesis. And planar diagrams, and we calculated duals. I should explain what a dual is. If you, for example, take the dodecahedron, or you take any of these, and you draw points in the center of each face and draw straight lines inside the object connecting those points, you get another one of the figures. And that's called a dual transformation, and it works the other way too. So if you take the one that you get that way and draw points in the center, straight lines, you get back to the first one. These are dual in pairs, except for this one, which is self-dual. So dual things were invented by Euler again, when Euler solved the bridges of Königsberg problem, which I don't have time to go into here, but Euler did it. And then sort of my last paper in particle physics was about something that has still not been observed. I should say the Z that I talked about, that has been observed now. 20 years later it was seen. And its mass is the same as, if you look in the periodic table for an element that number starts with Z, it so happens to have the same mass, just coincidentally, as the Z0. And that is 92 times the proton mass. And that's zirconium. So zirconium and that elementary particle that's like a heavy photon has the same mass. But this is about magnetic monopoles, and those have still not been seen. Dirac was convinced that they should exist because it makes Maxwell's equations a lot nicer looking. But nobody's found it, and probably they don't exist. So that would be like having a magnet with only a north pole, no south pole. And they scatter along cones, and if you look at the angular distribution coming out, you get rainbows and glories and all the things we like with water droplets. While I was at Syracuse, I started making astrolabes, and I still make those today. And I'm going to offer one as a reward for somebody who solves the following puzzle. I'm going to show you now. And if you've seen this puzzle before, then you're disqualified. So if you just remember seeing this, please don't tell the answer. I want somebody who's never seen it to solve it. So here's a series, just like the ones that Euler liked to sum up. And what you see there is 1, 2, 3, 4, 5 terms. And there's a 6th term. And of course, you could continue it indefinitely. And the question is, what is this term starting with these? And if you know the answer, or think you know the answer, then I'll pass you this pad of paper and you can write the answer on it. You know it? And have you seen it before?
I think so. I've seen a lot.
If you've seen it before, you're disqualified. Sorry. Okay. You know the answer?
But it's an obvious answer, isn't it?
You know the answer?
I think so.
Have you seen it before? Okay, then please write what you believe the answer is on this piece of paper.
Okay. I have not seen it.
Don't show anyone else.
I have not seen it before, but
Okay, we'll get you to write it also. Yeah. Okay, he was correct. Have you seen it before?
I mean, it sort of stands out.
Sorry?
It sort of stands out.
Don't say what it is now. That's correct. Okay, we have a third winner, and then I'll show you what it is. You see it?
I've never seen it before.
So you have the answer also.
Yes.
Okay. Who was it over here? Who? Okay. So just draw it on here. Don't show anyone else. Just write it on there. Okay. Thank you. Okay, Charles, I'm sorry, but I'm just going to take those first 3 winners. So if those winners could come up afterwards. And now what I'm going to do is not tell you the answer, but I'm just going to write the question differently. And those who have not seen it before, I think will see it now. So the answer is still not there, but I've added some red lines. And you could view those red lines as if they're mirrors. Okay, who sees the answer now? Some hands starting to come up. Okay, so if those red lines are mirrors, that's like me looking at myself in the mirror, right? So the mirror and the reflection are redundant. So imagine what you're looking at without them. Who sees the answer? Okay, who doesn't see the answer? Yeah, okay. Okay, so again, look at the picture and imagine that one or the other of those is a reflection. And imagine the picture without the reflection and without the mirror. You have to imagine it. Now, does anyone see it who didn't see it before? Okay, some folks still don't see it. So let's just take this first one. This is a mirror, and let's say that the thing on the left is a reflection. So imagine you're only seeing this on the right. Only this. Same thing here, you're only seeing this. Same thing, only seeing this, and only this. Now do you see it? Okay, I hope some of you have had an aha experience at this point. This is from a book by Martin Gardner. The title of the book is Aha. Now sometimes when you have an aha, you're actually wrong. I mean, a good example of that is I have a baseball bat and I have a baseball bat, baseball. And the baseball bat and the baseball together cost $1.10, and the bat is $1 more than the baseball. How much does the baseball cost? Answer?
10 cents.
Okay, so I heard the wrong answer and the right answer. So some people maybe have seen this before. But a lot of times you see that question, you will jump, and I would have jumped, to 10 cents. Because you'd say one's $1 and one's 10 cents. But if one's $1 and one's 10 cents, then the difference between them is not $1. Because the question was, one is $1 more than the other. So you actually have to do the math. Do the math. And so sometimes your brain will jump to an answer, and it's the wrong answer. So just because when I was a kid I'd stare at it and I'd get an aha, and I'd write it down, well, in the case of the geometry test, I happened to get them all right. But sometimes I'd jump to that with intuition, and it'd be wrong. So you have to calculate. Here I stared at the astrolabe and I said, here I had the right intuition. I said, those things all look like circles, even though they're not concentric. Every curve on there looks like a part of a circle or a whole circle. And I said, how can that be? Because this is a stereographic projection. And to make that, you imagine a sphere, and you attach a plane to the south pole of the sphere, and then you draw straight lines from any point on the sphere down to the South Pole, and, sorry, I should have made the plane go through the equator, and draw a line to the South Pole, and where that intersects the equator, that's a projection, a stereographic projection. But then if you imagine a circle on the sphere, and you draw all the straight lines, now you have a circular cone being cut by a plane, and that's not usually a circle, right? That's what? An ellipse. That's a conic section. The only thing is, it's not a right circular cylinder. It's a angle circular cylinder, not a right circular cylinder. And it just turns out the angles are correct, so that it is a circle. And this is an elementary proof of that. It uses the property of circles, which is invariance property, which is that if you have an arc on the circle, some tending a certain angle at the center, call it angle A, and you draw lines from the 2 points on that arc, the 2 endpoints, to any point on the circle at all, any point at all, then those 2 longer lines make an angle of 1/2 the angle you have at the center. So if you move that other third point around on the circle, you always get the same angle. Doesn't matter where it is. It's an invariance property. In fact, you can define a circle that way. That's a very cute thing. And it turns out you can apply that with some spherical geometry to prove that circles go to circles under stereographic projection. So those 3 people who got the answer to that one, your reward is to get an astrolabe that I made. So if you just come up afterwards, you'll each get an astrolabe. Okay, so there's just one other thing that I want to jump to here. Well, first I want to mention Maurice Blackman, who was my colleague in particle physics at Syracuse, and then he helped me transition to atmospheric science. He took over the advanced study program at NCAR from Mike Wallace, who had been a grad student with him at MIT, and Mike went off to Washington. And Maurice then brought me to NCAR, and that's how I made the change. I don't know if you recognize any of these other characters here. This is Eric Barron. This is Warren Washington. Claire left, I guess, but Claire knows him very well. This is Maurice and Mike this summer. Maurice passed away in August, so this is them drinking some wine there in Boulder. And this is me and my wife and 2 sons around the time that I went to Boulder. And then Jerry North had hired me also at University of Missouri, and where I was allowed to teach climate by studying it and staying ahead of the students, and so learned it there. Then Jerry came here to Goddard while I went to NCAR, and we wrote a couple of papers together there. And then Jerry brought me here. And this was one of the papers we wrote, a stability theorem for energy balanced climate models. And it basically, Michael Gill was a reviewer, and he made me put that word theorem in there. I didn't really want to put it in there, but I wanted to just say small ice caps are unstable. So, in fact, both small ice caps and large ice caps are unstable. It's only medium-sized ones that are stable. And that's often true with stability, that if you have nonlinear systems with multiple stable points, they sort of alternate stable, unstable, stable. And I'll show you an example of that.
What's an ice cap?
An ice cap is Greenland, for example, is an ice cap.
Isn't it?
And Antarctica is an ice cap. The sea ice in the Arctic Ocean is not an ice cap, it's floating ice. So anyway, the ice is unstable due to ice albedo feedback for Greenland because it's small enough that it's unstable. So I just want to show you a stability demonstration. Here's an empty box. It's a rectangular. And it has three principal moments of inertia that you can see very easily. So one is through the long axis of the box, the long symmetry axis, and you can rotate around that axis. Another is through the shortest, through this direction, if you imagine an axis, and you can rotate around that axis. And then the third one is through the intermediate direction, you can rotate around that axis. Now if I rotate around the short end, it's stable, no problem. Of course it's almost like a frisbee, I could probably spin it back there. If I rotate around the long end, there's no problem, it's stable. And now I'll ask this young man to rotate it around the intermediate one. It should be quite easy. I already did it around the long one. Stand up, please, and turn around. And it's very easy because I did it around the long one and the short one, and so the intermediate one should be kind of intermediate difficulty. So in other words, the axis goes through the intermediate thing, and I want you to rotate it up in the air this way.
Okay.
And just spin it so that it, no, not so it flops like that, but so it just goes around smoothly. No, smoothly, please. Maybe spin it a little faster. Can't do it? Okay. So that's an example of an instability that's kind of the one in the middle. Ice caps are the other way around. The one in the middle is stable. The ones on either end are unstable. So that was an early paper on that. And of course, now we're seeing that beginning to happen. This is just the sea ice shrinking back, and it's not quite got all the way to Greenland at the minimum. Once it gets right up against the coast of Greenland, I think we're going to see some faster changes. Now this one's about the dripping faucet, and that's my younger son there. He now works for the Nature Conservancy, and he built, with the help of Henning Leidecker, who's shown there. Henning is an expert on electronic whiskers, and I'll let Henning tell you what those mean, whiskers. But this is a bunch of plots of the time interval between a group of 1,000 drops dripping down from a faucet, the time interval between any two adjacent drops coming down, and on the vertical, the next time interval. So plot between drop 503 and 504, and then 504, 505. Those two intervals make 1 point on there. And so what you're seeing is some strange attractors. And the little insets there are from a different group at UC Santa Cruz that did a similar experiment and found the same shape of fractals. And my son and I enjoyed, he was a freshman in high school at the time, and we enjoyed kind of making up names for these. And the one in the upper left we called the cobra, and the one in the upper right we call the adders. And then of course there's the ring, and this one just below the upper right one, that's the ostrich. We just made these up. And then there's a window in which you get a triplet. So dot, 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 dot. And actually, I guess I'll just try to use the drum here to show what happens. And this one we call the phoenix. That's the phoenix. So you find all those same sets with any dripping faucet, any size, with a nozzle shaped in different ways. So they're universal. And there are other ones too. The simplest one looks like a parabola, except when you zoom in on it and it becomes a ribbon, a twisted ribbon. And you zoom in on the ribbon, it has 3 stripes on it. And you zoom in on one of the stripes, and that stripe resolves into 3 smaller stripes. And so each of these is fractal, if you keep zooming. So, but what happens first is you start with a really slow dripping, and you get periodic. So imagine just water dropping on the drum, just periodic. And then you speed it up, and at a certain point, each of the drops gets a satellite. And then each of those drops gets a satellite. I don't know if I can do this one. And then you get into chaos. So then it just, something like that is chaos. And then at a higher drip rate, it becomes a triplet. And then you can also see one with 4 different groups there. So there are periodic ones. And this is something that Ed Lorenz had studied earlier. Oh, by the way, you can take 2 points close to each other on an attractor and look at the series of drops, and they stay together for about 12 drops, and then they diverge. So there's some predictability, similar to weather. Lorenz knew about this beginning at least in 1964. He wrote this paper on deducing the climate from governing equations, and he had used a simple logistic equation, which is the equation you get for the parabola. Actually, we found when we zoom in on the parabola, it becomes the Henon attractor when it becomes a ribbon. But anyway, so he looked at this and he said the mean of the climate goes like that until you get to 3 point something. You get to some number. He shows it there, 1 plus the square root of 6. So that's, imagine the pressure in the faucet. So remember this kind of curve, like in global warming? So here there's only a single parameter. It's sort of as if the climate was being driven only by the greenhouse forcing, nothing else, no El Nino or anything else. It's nonlinear. Now you see the one little dot there. That dot is super chaos. And in between where the line ends and the dot, you zoom in and you get this kind of behavior. So it could be that when Greenland really starts to go, we will no longer even have straight lines in the warming. We're going to have extreme cooling followed by a super warm period and just things bouncing around quite a bit. This is what this kind of simple dynamical system does. And I'm sort of going to skip through the fractal part because I don't have much time for that, but I just want to show one thing, and that is that we found that the effective liquid water we should use to get the albedo correct for clouds is the mean liquid water divided by the square root of Euler's constant E. So Euler comes in again, and that turns out to be about 70% of the mean. So if you reduce the liquid by about 30%, that's what you get. Actually, there's an appendix in there where we derive the moments of a fractal model that's in there, and we ended up having to use Euler's equation. It turns out Euler had actually done what we call now the bounded cascade. He'd done that back in the 1700s, but he didn't think of it as being for clouds. It was just something that helped him count partitions of integers. Here are the clouds. So here are, you should look at those and you should see angel hair and ice cream castles. Do you see them? And of course, we assume that clouds are uniform and plane parallel. This is from a laboratory experiment that we did. Remember this, John? We did this thing with a little probe there, and we saw halos. When we shined a laser on it, we saw halos. And we found that the size of the halo depended on how thick the layer was. Remember this group here? Really it was John and Matt McGill who built the Thor system that's based on that idea, but also Anthony Davis and Luis Rodriguez Izquierdo. Luis designed the optical system that we used in that, which has massive fiber bundles, so a multiple field of view looking at the return from a laser. And we found that by looking out at the edge of the halo, we could determine how thick a layer of cloud, 1 kilometer thick, we could determine the thickness to 5%. So that's Thor. And by the way, that picture of Guyong Wen on the left there is on a Hawaii on a lava flow. And John, you might remember that meeting on Hawaii where we were kind of guided around across the flow. That's Hiroko Miyahara there, who's worked with us on the sun and the moon. And I'll just show that when you zoom in on the sun, and I'll zoom in until we have a field of view the size of the Earth, then you also see 3D effects in the sun once you're able to resolve the individual the individual kind of convective cells. So the Earth would fit barely inside that window there. And if you look around the edges of those little, you could think of them as clouds on the sun, but really it's convective cells, you see 3D effects, and people doing the radiative transfer near the surface of the photosphere find they have to take account of 3D effects. So there's that one, we already did that. There's the answer, in case some of you hadn't seen that before. And of course it's obvious the next one would just be a reflected 7, reflected 8. You could continue it indefinitely with a mirror. And just one last one. The Pythagoreans loved this curve. They loved the pentagon because they said it was very symmetrical and had lots of nice properties. However, if you make the side of the pentagon equal to 1 unit, and then you just draw the line across, skipping one of the points, it turns out the length of that one going across is 1 plus the square root of 5 over 2. It's the golden ratio. And the Pythagoreans didn't believe in non-rational numbers. So the fellow who proved that this was non-rational was kicked out of the Pythagorean society because he didn't agree with their sort of religious beliefs about the way those numbers worked. If you draw the other lines, then you get a little pentagon in the center. And of course you could continue the thing with smaller and smaller pentagons, or you could extend the outer boundaries out till they meet a point, and then you get larger and larger pentagons. So you actually have a fractal there with an infinity of scales, you can imagine, just by continuing that. And of course the Pythagoreans didn't think that way either. They thought they could make an atomic theory out of these simple polygons. Similar to Kepler, who thought he could make a theory of planetary orbits out of the regular polyhedra just by inscribing and circumscribing spheres. So Kepler didn't like the ellipse and stuff, even though he discovered it. He liked the beautiful geometrical pattern. So I'll just sort of end there with a quote from Robert Frost, the woodpile, who kind of looks back on his life in walking through the woods and kind of wonders whether people would be interested in any of the things that he's done in his past life. And this bottom one is a quote from Neil Young's autobiography that just came out recently, and I think this is relevant to those of us who have to keep track of our time and are often told that science is all about money. And you have to make the money, otherwise you can't do the science. But really, that's not what motivates us, right? And same as what Neil Young is saying, he doesn't do music to make money, even though that was a side effect of what he was doing. So I'm with him on that. And I'll just end it there with...
Okay, let's keep going. Sorry we went beyond the allocated time, but he spent a lot of time preparing these experiments, and I thought I should just let it go. So any 1 or 2 questions before we end it?
I want to show you one other thing real quick. This is a spinner. A spinner is something which, if you rotate it once around 360 degrees, it doesn't come back to where it was before. But if I rotate this 360 more degrees in the same direction, it will come back to where it was before. So rotations are double valued. Now you may think, I can't really do that, right? Because I'm going to break my arm. But watch this. Watch, I'm going to start here, and just watch the cup handle carefully, because it's going to rotate twice around, all in the same direction. So here's once. Oops. And there's twice. And it's right back to where it was. It's a spinner. And that's also the basis of what some people call the Hungarian handshake, but I won't show you that.
So with that, let's give